For centuries, our understanding of gravity has been shaped by the groundbreaking work of Isaac Newton and Albert Einstein. Newton's law of universal gravitation provided a mathematical framework to describe the force of attraction between objects with mass. Centuries later, Einstein's general relativity revolutionized our understanding of gravity, describing it not as a force, but as a curvature in the fabric of space-time caused by mass and energy. But what if this picture is incomplete? What if, at the most fundamental level, gravity is not just about curvature, but about something more dynamic, something inherent to the very essence of space-time itself? This is where the concept of Inherent Curvature Dynamics, or ICD, emerges, offering a tantalizing glimpse into a new era of cosmological understanding. ICD proposes that the curvature of space-time is not merely a passive response to the presence of matter and energy. Instead, it suggests that curvature itself possesses an inherent dynamism, a kind of internal energy that drives the evolution of the cosmos. Imagine the universe not as a static stage upon which the cosmic drama unfolds, but as an active participant, its very fabric in constant flux, shaping and being shaped by the interplay of fundamental forces and particles. This dynamic nature of space-time, as envisioned by ICD, has profound implications for our understanding of the universe. It offers new perspectives on the expansion of the cosmos, the nature of dark energy, and even the origins of the universe itself. Just as Einstein's theories extended our understanding beyond Newton's framework, ICD has the potential to usher in a new era of cosmological thinking, pushing the boundaries of our knowledge about the universe and our place within it. At the heart of ICD lies a radical departure from conventional cosmological models. It challenges the notion of a static cosmological constant, a fixed value representing the energy density of empty space. This constant, often denoted by the Greek letter Lambda, has been a cornerstone of modern cosmology, used to explain the observed accelerated expansion of the universe. However, ICD proposes a more dynamic picture, suggesting that Lambda is not a constant at all, but a variable entity, influenced by the complex interplay of fundamental forces within the universe. Imagine the cosmological constant not as a fixed dial, but as a fluctuating gauge, its needle responding to the ebb and flow of gravitational energy and the quantum fluctuations of space-time itself. This dynamism, according to ICD, arises from the interaction between two fundamental forces: the gravito-strong and gravito-weak forces. These forces, theorized to be remnants of a unified force that existed in the earliest moments of the universe, continue to exert subtle but profound influences on the fabric of space-time. The gravito-strong force, as its name suggests, governs the interactions within the quantum realm, influencing the behavior of quarks and gluons, the building blocks of protons and neutrons. The gravito-weak force, on the other hand, acts as a bridge between the quantum world and the macroscopic universe, linking the behavior of fundamental particles to the curvature of space-time itself. Within the framework of ICD, these forces are not isolated entities, but engage in a delicate dance, their interplay influencing the value of lambda, and consequently, the expansion rate and overall evolution of the universe. This dynamic interplay, where the very essence of space-time responds to the dance of fundamental forces, lies at the core of ICD's vision of a universe in constant flux, a universe where gravity is not just a force, but an active participant in the grand cosmic drama. One of the most perplexing discoveries of the 20th century was the realization that the universe is not static, but expanding at an accelerating rate. This discovery, based on observations of distant supernovae, upended our understanding of cosmology and introduced the concept of dark energy, a mysterious force that seemingly counteracts gravity, pushing the universe apart. The standard model of cosmology attempts to explain this acceleration through the cosmological constant, a fixed value representing the energy density of empty space. However, this explanation raises more questions than it answers. Why does empty space possess energy? What determines the value of the cosmological constant? And why is its observed value so incredibly small, yet non-zero? ICD offers a compelling alternative to the static cosmological constant by proposing that the energy density of spacetime is not constant but dynamic. Instead of being a fixed value, lambda fluctuates in response to the interactions of fundamental forces, particularly the gravito-strong and gravito-weak forces. These forces, remnants of a unified force that governed the universe in its earliest moments, continue to exert subtle but profound influences on the fabric of spacetime. The gravito-strong force, operating within the quantum realm, affects the energy density of spacetime at the smallest scales. Its influence, though minute on macroscopic scales, can, when integrated over the vastness of the universe, contribute to the observed acceleration. The gravito-weak force, bridging the quantum and macroscopic realms, provides a mechanism for these quantum fluctuations to influence the overall curvature of spacetime, further contributing to the dynamic nature of lambda. In this way, ICD suggests that dark energy is not a mysterious, independent entity, but an emergent property of the dynamic interplay between spacetime and the fundamental forces that govern it. The revised framework suggests a need to reconsider the existence of dark matter. Gravitational phenomena typically attributed to dark matter, such as galaxy rotation curves, structure formation, and gravitational lensing, could instead be the result of torsion curvature coupling, amplified through gravito-strong and gravito-weak fields. This amplification not only facilitates large-scale cosmic inflation, but also drives localized inflation in high-energy environments, such as quasars, where extreme torsion curvature interactions are observed. In these high-energy regions, gravito-strong and gravito-weak fields could mimic gravitational effects commonly associated with dark matter, thus potentially eliminating the need for an independent unseen matter form. In regions with intense torsion curvature interactions, such as quasars, gravito-strong and gravito-weak fields may generate localized inflationary effects, gravitational anomalies, or even unique gravitational wave signatures. These phenomena could serve as observational evidence of the ICD framework. Additionally, the evolving nature of dark energy within this model could offer a solution to the Hubble tension, the discrepancy between locally measured and early universe inferred values of the Hubble constant. As dark energy varies over cosmic time due to fluctuations in curvature and torsion, subtle changes in the expansion rate may emerge, providing a plausible explanation for this tension. The ICD framework predicts unique gravitational wave signatures from areas of intense torsion curvature coupling. Gravitational waves produced in high-energy environments like quasars or primordial waves from the early universe could carry distinctive imprints of these interactions, offering an additional observational test for this theory. The accelerating expansion of the universe, rather than being driven by an unknown force, becomes a natural consequence of the inherent dynamism of spacetime itself. Within the ICD framework, Goldstone and pseudo-Goldstone bosons play crucial roles in symmetry preservation within quantum soil. These bosons help maintain spacetime structure, interacting with the gravito-strong and gravito-weak fields to uphold symmetry without leading to inflation. Through these interactions, they support quantum soil's cyclic properties, fostering cosmic regeneration and continuous evolution. Spin-zero Goldstone bosons, as massless scalar particles, emerge from spontaneous symmetry breaking, maintaining symmetry within quantum soil. Goldstone bosons stabilize torsion curvature interactions within quantum soil, preserving symmetry without contributing to inflation. Pions, as spin-zero pseudo-Goldstone bosons, mediate the strong nuclear force at low energies and interact with the axial vector current. In quantum chromodynamics, QCD, pions acquire a small intrinsic mass due to explicit chiral symmetry breaking. In ICD, pions exhibit mass-like gravitational effects through their indirect influence on spacetime's torsion curvature structure within the gravito-strong and gravito-weak fields. This influence is vastly smaller than their QCD mass, on the order of ultralight particles, representing an indirect gravitational influence rather than a true rest mass. The accelerating expansion of the universe, rather than being driven by an unknown force, becomes a natural consequence of the inherent dynamism of spacetime itself. To fully grasp the implications of ICD, we must delve deeper into the quantum realm, where the very fabric of spacetime is woven from the threads of quantum fluctuations. Here we encounter the concept of quantum soil, a theoretical framework that underpins ICD's vision of a dynamic and interconnected universe. Imagine the quantum vacuum, often depicted as empty space, not as a void but as a seething sea of virtual particles, constantly popping in and out of existence. This quantum foam, as it is sometimes called, is not merely a theoretical construct, but has observable consequences. For example, the Casimir effect, where two uncharged, perfectly conducting plates placed in a vacuum experience an attractive force, provides experimental evidence for the existence of this quantum vacuum energy. Quantum soil takes this concept a step further, proposing that this sea of virtual particles is not random, but possesses an inherent structure, a kind of quantum grain that influences the behavior of fundamental particles and the curvature of spacetime itself. This grain, according to ICD, is influenced by the gravitation force, which acts as a kind of cosmic gardener, shaping the distribution of quantum fluctuations and, consequently, the properties of spacetime. The gravitation force, by influencing the arrangement of quantum soil, effectively determines the fertility of spacetime, influencing its ability to support the formation of particles, the propagation of energy, and the overall curvature of the universe. This concept of quantum soil, intricately linked to the fundamental forces of the universe, is central to ICD's explanation of various cosmological phenomena, including the observed inhomogeneities in the cosmic microwave background radiation, the remnant heat signature of the Big Bang. These inhomogeneities, subtle variations in the temperature of the CMB across the sky, have long puzzled cosmologists. ICD suggests that these variations could be remnants of the primordial structure of quantum soil, imprints of the early universe's quantum fluctuations frozen in time.